Today I start on important topics related to vector subspace. Okay, so we're also going to discussion about the subspace in previous class. We also discuss this subspace, and obviously we also give so many examples related to matrices of that means which one are subspace or not. Today we also start from that examples, okay, of subspace. So we start from examples of subspace. Okay, first we write let n be a non-negative integer. Be a non-negative integer. Okay, then what happened? Let P and F be consist of P and F consist of all polynomials in Pf of all polynomials in Pf. Okay, having degree less than or equal to n. Having degree less than or equal to n. Okay, then what happened? Then we also going to be discussion of that since the zero polynomial has degree -1, since the zero polynomial has degree -1, okay, it is in P and F. It is in P and F. Okay, now we are also going to discussion of that the sum of two polynomials with degree less than or equal to n. The sum of two polynomials okay, with degree less than or equal to n, with degree less than or equal to n, then what happened? The sum of two polynomials with degree less than or equal to n is another polynomial. Okay, is another polynomial of degree less than or equal to n, of degree less than or equal to n, okay, then what happened? And the product of a scalar and a polynomial of a degree less than n, the product of a scalar and a polynomial of degree less than n, a polynomial of degree less than n, okay, what happened? Less than or equal to n, then what happened? Obviously is a polynomial of degree less than n, or equal to a. Okay, or equal to a. Understood? Then what happened? Then obviously that means so P and F is closed under addition and scalar multiplication. Okay, so P and F is closed under addition and scalar multiplication and scalar multiplication. Okay, addition and scalar multiplication. So what happened? Then we also talk about that this one P and F. Okay, P and F be a subspace. P and F be a subspace of PF. Be a subspace of PF. Okay, understood? I think all are understood that portion. Not a problem at all. Let n be a non-negative integer. Phi and f consist of all polynomials in phi f having degree less than or equal to n. Since the zero polynomial has degree minus 1, it is in P and F. The sum of two polynomials with degree less than or equal to n is another polynomial of degree less than or equal to n. The product of a scalar and a polynomial of degree less than or equal to n is a polynomial of degree less than or equal to n. So P and F is also closed under addition and scalar multiplication. So P and F be a subspace in PF. Okay. So we also discuss this subspace now. And now we erase that portion and going to further discussion of that. Okay. Here denote the set of all continuous real valued functions. The set of all continuous, okay, real valued function, okay, defined on R, clearly CR be a subset of the vector space FRR. Be a subset of the vector space okay, FRR. Okay, then what happened? Then obviously first we note that the zero of FRR, okay, the zero of FRR is the constant function defined by ft equal to 0. Okay, the zero of FRR be the constant function defined by what? Defined by ft equal to 0 where for all t belongs to R. Okay, then what happened? Then obviously since constant functions are continuous, so we have f belongs to CR. Since constant functions are continuous, So we have what? We have A belongs to CR. Okay, understood? So that means what we also did, that means right now, that means A belongs to CR. Now the sum of two continuous functions, and that means 0 of f are obviously in CR. Okay, now now we're also going to discussion about that sum of two continuous functions. Okay, sum of two continuous function be continuous. Okay, be continuous, and what happened, the product of a real number and continuous functions is continuous, and the product of a real number and the product of a real number and the product of a real number and a continuous functions and a continuous function be continuous. Okay, be continuous. Then what happened, then obviously CR, so CR closed under addition and scalar multiplication. So CR closed under addition and scalar multiplication, under addition and scalar multiplication and scalar multiplication. Okay, addition and scalar multiplication, and hence okay, and hence this one obviously be a subspace of if R. Hence CR, okay, be a subspace of if R. Understood or not? So we also discuss this one too easily. Okay, I think all are understand this too easy problem, which are, that means satisfies this set of all continuous functions, real valued continuous functions defined on R, obviously be subspace on the set of all functions from R to R. Okay, and obviously the set of all polynomials of degree n obviously be a subspace of the set of all polynomials. Okay, next we're going to discussion about some, that means familiar example which are not subspace. Okay, then we going to one important theorem, so we erase that portion and going to further discussion of that. Okay, example the set the set of matrices in n cross n are, okay, having non-negative entries, having non-negative entries having non-negative entries, okay, is not a subspace of is not a subspace of n cross n r. The set of matrices in n cross n are, okay, having non-negative entries is not a subspace of n cross n r because it is not closed under scalar multiplication. It is not closed under scalar multiplication. Okay, so we also, that means the set of all matrices having non-negative entries, okay, is not subspace. Why? Because it is not closed under scalar multiplication. Okay, that means all are non-negative entries, but if we, that means, enter the multiplied by some that means element from field, this one is some negative element, then this, all entries are negative, so this one not belonging to the set of all matrices having non-negative entries. So we also see, so that this one is not closed under scalar multiplication. Okay, so now we discuss one important theorem related to this subspace. Okay, any intersection of subspace of a vector space V, we also talk about that. Any intersection of subspace of a vector space, of subspace of a vector space, V, okay, is a subspace of V, any intersection of subspace of a vector space is a subspace of V. Okay, we also discuss this theorem too easily. Understood? We write this proof now. Let's see with the collection of subspace of V. See with the collection of subspace, okay, subspaces of V, and let W denotes the intersection of subspaces, denotes the intersection of the subspaces in C, of the subspaces in C. Okay, since every subspace contains the zero vector, so 0 belongs to V. Okay, Let's see with the collection of subspace of V, and W denotes the intersection of subspaces in C. Okay, since every subspace contains the zero vector, since every subspace contain the zero vector, contain the zero vector. Okay, every subspace contain the zero vector, then what happen? Okay, then 0 belongs to W, then 0 belongs to W. Okay, any intersection of subspace is a subspace. How we prove that? That means we also discuss in this way. We also first talk about that. Let C be a collection of subspace of V, and W denotes the intersection of subspace in C. Since every subspace contains the zero vector, then 0 belongs to W. Okay, not a problem at all. Now we, that means right here in this way, that means what is happen here, let A belongs to F and XY belongs to W. Let A belongs to F and XY belongs to W, and XY belongs to W. Okay, then what happen? Then in this way we also, that means so that A belongs to F and XY belongs to W. Then in this way we show that then X and Y are contained in each subspace in C. Then X and Y are contained in each subspace of C. Okay, in each subspace in C. In each subspace in C. Okay, in each subspace in C. Then what happened? Because each subspace in C, we erase our portion and going to further discussion of that. Then what happened? Then X, Y are contained in each subspace in C. Okay, because each subspace in C is closed, because each subspace because each subspace in C, okay, in C closed under addition, is closed under addition and scalar multiplication okay, closed under addition and scalar multiplication, it follows that, okay, it follows that x plus y and ax are contained in each subspace in C. Okay, x plus y and ax are contained in each subspace of C, are contained in each subspace in C. Okay, then what happened? Then obviously hence x plus y and ax are also contained in W, are also contained in W. Okay, so that W is a subspace of V. So that W is a subspace of V. Understood? Not a problem at all. So we also done this. Any intersection of subspace of a vector space V is a subspace of V. Okay, let's see with a collection of subspaces of V, and W denotes the intersection of subspaces in C. Since every subspace contains the 0 vector, then 0 belongs to W. And this one, A belongs to A, X, Y belongs to W, then X and Y are contained in each subspace in C. Because each subspace in C is closed under addition and scalar multiplication, it follows that X plus Y and AX are contained in each subspace in C. Hence X plus Y and AX are also contained in W, so that W is a subspace of V. Okay, so we also prove this important theorem. Any intersection of subspace of a vector space V is a subspace. Okay, we also prove that important theorem, and obviously we know about that. That means union of subspace is not need not be closed under addition. Okay, but union of two subspace is a subspace of V if and only if one of the subspace contain the other. Okay, then this one is possible, otherwise not possible for union. So that means we also write it now, not prove that portion. Okay, we erase that portion and go into further discussion on that. Union of subspace spaces of V need not be closed under, need not be closed under addition. Okay, union of subspace R of V need not be closed under addition. Okay, then we also talk about that the union of two subspaces, the union of two subspaces. Okay, the union of two subspaces of V need not be closed under, need not be closed under addition. Okay, union of two subspaces of V need not be closed under addition. Okay, so we talk about that union of two subspaces of V is a subspaces of V. Okay, not here, is a subspace, is a subspace of V. Okay, is a subspace of V if and only if and only if, okay, one of the subspaces contain the other, one of the subspaces contain the other, contain the other. Okay, one of the subspecies contain the other. Then what happened? Two subspecies W1 and W2 to obtain a subspace that contains both W1 and W2. Okay, two subspecies W1 and W2 are to obtain a subspace that contains both W1 and W2. Okay, now we also going to discussion of some important, that means proof. Okay, also known about that, that means upper triangular matrices. Okay, upper triangular matrices we also known about that. Now we write the definition of upper triangular matrices. Okay, so we write this definition now. Okay, if we talk about how this one is formed, okay, then we also, then we have to give some discussion about that. Okay, that means union of two subspace is a subspace of P. Then if one of the subspace contain the others, if here we have to then give some example, and here we have to give some proof of that. But today we will not discuss, we just discuss this upper triangular problem, upper triangular matrix definition. Okay, and M cross N matrix. Okay, in M cross N matrix, A is called upper triangular matrix, is called upper triangular if all entries if all entries lying below the diagonal entries are 0. All entries lying below the diagonal entries are 0. Okay, that is in this way, if Aij equal to 0 whenever I greater than j. Okay, whenever I greater than j, this one is happen. Understood? And the set of upper triangular matrices from a subspace of M n cross n if. Okay, the upper triangular matrices okay, the upper triangular matrices from a subspace of M cross n A. Understood? Not a problem at all. So today we also discuss so many examples and of subspace and related theorem of subspace, and obviously some basic definition of subspace and some related, that means problems in subspace. So today I stop here. Okay, if you get this type of videos, please subscribe my channel, and if you gather some knowledge about these topics, then obviously please see these videos, and obviously that means subscribe my channel. And next, if you have some comment, questions, suggestions, write in comment box, and if you give like, please click on like options. So today I stop here. Thank you.